Okay, so now we want to solve this PDE. And as I mentioned, the interesting thing going on here is that it's a quasi-linear PDE. And also, as I mentioned, that's going to be a 2. This will be a 1. And that will be a 2. So this is an initial value problem because we know the initial distribution when t is equal to 0. We call a problem like this a Riemann problem. Whenever the initial data is discontinuous like this. Okay, and so we're just going to use method of characteristics. And remember that z of s is still going to be rho of x of s t of s. So t dot, we're going to say, is just whatever is multiplying the t derivative of rho, which is 1, and t of 0 is 0. X dot is going to be whatever is multiplying the x derivative of rho, which is rho, but z is equal to rho, so this is going to be equal to z. X of 0 is going to be x naught. And then z dot, well again, by the chain rule, z dot is going to be equal to x dot times the x derivative of rho plus t dot times the t derivative of rho. And given what we have for x dot and t dot, this is going to be z times the x derivative of rho plus 1 times the t derivative of rho. But that's just equal to 0 because, again, z is equal to rho and I'm using the characteristic or the PDE here. And again, z dot, when we do it this way, z dot is always going to be the stuff involving the derivatives of the unknown function. So z dot is going to be equal to 0, and then z of 0 is going to be equal to 1 if x naught is less than 0, and it's going to be 2 if x naught is greater than 0. Okay, so now notice the big difference here so far is that my equations for t and x involve z. In particular, the equation for x involves z. That's new. That's a new thing when we're dealing with quasi-linear equations. So let's just solve what we can. So if I look at my t equation, this is going to tell me t of s is equal to s. If I look at the z equation is z dot is equal to 0. So z of s is just going to be equal to z naught. And now I can plug that into my x equation. This gives me x dot is equal to z naught. So x of s is equal to z naught s plus x naught. Okay, so what does this mean? Well, remember, z naught is going to be equal to 1 if x naught is less than 0, and it's going to be 2 if x naught is greater than 0. Okay, and for my x equation over here, this will be z naught. I'll write this as a piecewise. It'll be s plus x naught if x naught is less than 0, and it will be 2s plus x naught if x naught is greater than 0. Okay, so now let's draw these characteristics. So this will be the t-axis, this is the x-axis, this is the t-axis. So let's draw the characteristics. So I'm going to kind of split this into two different regions here. So let me actually, just to have things color-coded, I'm going to do these characteristics in, let's say, red or purple. So this is 2s plus x naught for x naught greater than 0. Okay, so let me look at the top characteristic. I'll sketch these first. So these have equations x is equal to s plus x naught, but s is equal to t, so I can write this as t plus x naught. So then we might think, it might be easier to think about this as being in the form t is equal to x minus x naught. At any rate, it's going to be a line of slope 1, and it's going to go through the x-intercept is going to be x naught. Okay, and so this is going to be for all x naught less than 0, and I'm actually going to draw them all the way up to x naught is equal to 0. But I'm going to do this one. You'll see why in a minute. I'm going to do this one in a dashed line. And then all the other characteristics for x naught less than 0 are going to be here, and I'm going to draw them, in a solid line. They're going to be 45-degree angles, like this. Okay, slope is equal to 1. Okay, and what the PDE tells me is that the solution is constant there, and so I know over here in this region, rho is going to be equal to 1, because that's what over here, rho is equal to 1. Okay, now for the characteristics starting for x naught greater than 0, similarly we have x is equal to 2t plus x naught, and so I can write this as t is equal to x over 2 minus x naught. Okay, so again, we're going to have characteristics, or not again, but we're going to have characteristics that pass through the point, the x-coordinate is x naught, and the slope is 1/2. And now again, I'm going to actually, this is going to be for x naught greater than 0, but I'm actually going to sketch it for x naught equals 0. And I'm going to do that one as a dashed line as well. So the slope is 1/2. So I'm going to go over 2 and up 1. And we're going to get something like this. Here's another characteristic. I'll draw this filled in line. Okay, and again, for these purple characteristics, I know they go back to this part of the axis. Okay, and z is constant on these characteristics, and I know down here, rho is equal to 2, so that means in this part of the plane, in this part of the region, u is going to be equal to 2 for the purple characteristics. Okay, so now the problem that we face is, notice if I have, so in other words, if I have a generic point here, let's call this AB, I know that at that AB, u of AB is equal to 1, and then I know at this generic AB, I know u of AB is going to be equal to 2, and I can kind of write this, this is in the orange region, and this is in the purple region. Of course, we want to actually write this in a little, more mathy way, a more precise way involving inequalities. So it's going to be 1. Okay, so this orange line right here, this orange dash line right here, is t is equal to x. Okay, and so I know the solution is going to be 1. How can I write that orange region? That orange region is going to be t greater than x. So I know it's going to be 1 when t is greater than x. Whoops. I know it's going to be 1 when t is greater than x. Okay, if I'm in the purple region right here, well, this purple dashed line is t is equal to x over 2. And so it's going to be equal to 2 if t is less than x over 2. Okay, but what this leaves me now is what happens if t is bigger than x over 2? What happens if I have x over 2 is less than t, and t is less than x? That corresponds to this wedge region right here. And notice none of our characteristics pass through that region. So using the method we have so far, we can't really determine what the value of the solution is in that region there. And I realize I've just done it again. All of these u's here need to be rho. Okay, and I've got, sorry. All right, so this is what we have here. Okay, so what can I do about those, what can I do about the points in this plane right here? Well, there's going to be a couple of things we can do. We'll see why in later videos, but the best thing to do, the thing that is the most physically reasonable, like if this is modeling a physical situation, is to just imagine a line, we're going to call it a characteristic, that goes through the origin and through this point right here. And we're going to call this AB. Okay, so what is one of the, let's ask this question. What is a distinguishing distinguishing characteristic, or I say a distinguishing property about the characteristics. Well, let's look. What is the slope of a characteristic? The slope is going to be equal to the t derivative over the x derivative. So the slope satisfies m is equal to t dot over x dot. This is true for any characteristic at all. In this problem, t dot is equal to 1 and x dot is equal to z, but z is just equal to rho. So we've got m is equal to 1 over rho. Okay, so we're going to apply that property to this red characteristic. I know the slope of this red characteristic is b over a, or the slope of that red line that I'm calling a characteristic is b over a. So the slope is b over a, and this is equal to m. But if this is a characteristic, m is equal to 1 over rho. Okay, so now I'm just going to solve this for rho. So rho of AB is equal to 1 over m. Or I could just write this as a over b, because 1 over m is equal to a over b. And so that's what we're going to have over here. This is going to be x over t. If t is bigger than x over 2 and less than x. Okay, so when we have something like this happening, we call this an expansion wave. And the reason that we call this an expansion wave is because the distance between the two different solutions is going to be expanding. The difference between the rho equals 1 solution and the rho equals 2 solution is expanding. So if I look at a fixed value of t down here, I've got that distance there. If I look at a fixed value of t up here, I'm going to have a different distance. So the distance is expanding. Also, another way to think about this, the formula for this, pictorially, what's going to happen if I look at a fixed value of t, the graph is going to look something like this. For a fixed value of t, I'll talk a little bit more about this in the next video, but for a fixed value of t, what's going to happen? Well, in the beginning, so this is now the x-axis, and this is the rho axis. So in the beginning, rho is equal to 1 here, and it's equal to 2 there. And then what happens as t increases, we get something that looks like this. It's going to be 1 here. It's going to be, and I'll do something more precise in an upcoming video. It's going to be 2 there, and then it's going to be sort of linearly interpolated there. This would be the rho. This would be what rho is. Actually, this extends out this way, and this extends out this way. Okay, I'll say a little bit more about this in an upcoming video and draw some better pictures in this. But this is called an expansion wave. This is not, there's not a unique solution. In fact, I could do something like rho of xt is equal to 1 when t is bigger than x, is equal to 2 when t is less than x. This is also going to be a solution to the PDE. But we'll explain why in upcoming videos, we'll explain why this really isn't a good solution for this equation. This is kind of not a very physically reasonable solution, but we're going to have to look at shocks before we are able, so it's going to be a few videos before we can explain that. Okay, so for the next video, I'm going to explain this a little bit better, and then we'll get on to other stuff.